failure consequences, and proactive maintenance.
When we write our failure effects properly, that allows us to go to the next step in the RCM process, which is failure consequences. Do we have safety consequences, environmental, operational, or non-operational consequences? Then we get to step 6, which is proactive maintenance and associated intervals. And it's not lost on me that while I'm making this video, there are airplanes flying above, and like I mentioned, RCM was born in the airline industry, so let's just consider that a little synchronicity from the universe. So when it comes to step 6 with proactive maintenance, that includes condition-based maintenance, and it includes preventive maintenance. So condition-based maintenance, where we may want to, if we go back to our bearing, where we may want to monitor for vibration and schedule replacement of the bearing when it needs it. And we could do that with a sophisticated device, or we could use our human senses.
Let's discuss proactive maintenance in more detail. In the context of reliability-centered maintenance, in order to schedule a condition-based maintenance task, or in other words, an on-condition task, a scheduled restoration, or a scheduled replacement task, 2 criteria must be satisfied. The task must be technically appropriate, and it must be worth doing. Let's look at what that means, starting with scheduled restoration and scheduled replacement tasks. One of the most important elements that makes a scheduled restoration or a scheduled replacement task technically appropriate is that the likelihood of failure increases with operating age. In other words, there's a useful life. Let's take a look at the failure pattern that depicts this, and let's break it down so it's easy to understand. The x-axis is age, which can be expressed in any number of units, such as days, weeks, or operating hours. And the y-axis is the conditional probability of failure. On this failure pattern, you can see that the probability of failure as age increases is constant in this region until it reaches this particular age. And then the probability of failure starts to drastically increase. An example of a scheduled replacement task is having the oil in your car changed on a scheduled basis. After a certain amount of miles, say 7,500, we know that the oil's properties become depleted and it won't be able to lubricate the engine components properly. It's obviously worth having the oil changed at 7,500 miles because it's cheaper to change the oil on a scheduled basis than to allow the engine to be damaged because it's not lubricated properly. In the context of RCM, scheduled restoration and scheduled replacement tasks are considered preventive maintenance because action is taken before failure is allowed to occur. Now let's move on to condition-based maintenance, or on-condition maintenance. We know that most failure modes occur randomly, approximately 89%, and that's one of the reasons why on-condition maintenance can be a valuable failure management strategy. We also know that most failure modes provide evidence that failure is in the process of occurring. This evidence is called a potential failure condition. For example, vibration, heat, wear, and gauge indications. An on-condition maintenance task is performed at a defined interval to detect a potential failure condition, so action can be taken prior to failure occurring. That way, maintenance is performed only on the evidence of need, and an organization gets the maximum useful life out of a component. On-condition maintenance task intervals are determined based upon the P2F interval. This is the P2F curve. The x-axis is time, which can be measured in any units such as calendar time, operating hours, or miles. The y-axis is the resistance to failure. The time that a new component is installed is depicted at the top of the y-axis, indicating the maximum amount of resistance to failure. As most components remain in service, the resistance to failure declines, and eventually a sign of impending failure is exhibited. In other words, a potential failure condition develops. A potential failure condition is represented by P. If the potential failure condition goes undetected and we don't intervene, eventually failure occurs. Failure is represented on the P to F curve as F. The P to F interval is how long we have from when the potential failure condition is detectable to the point that failure occurs. The P to F curve is incredibly valuable because on-condition maintenance task intervals are determined based upon it. On-condition maintenance task intervals are performed at intervals less than the P to F interval, as long as the time remaining is long enough time to take action. All of this makes an on-condition task interval technically appropriate. If it costs less to do the on-condition task than to run it to failure, in monetary terms or risk, then the on-condition task is worth doing. One key idea to take away from this is that CPM task intervals are based upon how quickly failure occurs once the potential failure condition is detectable, not how often the failure occurs.